So hello friends, welcome back to our channel. Although this video was to be going live, but since there are some technical glitches going on with my channel, I'm not able to upload it. So as a result, I am making this recorded video so that we can finish the chapter seamlessly. So we have studied about a lot of periodic properties in the previous classes. We have studied about how they are dependent upon the nuclear charge and also the atomic size. Today we are going to learn about the three most important periodic properties, namely ionization potential, electron affinity and electronegativity. So let's begin. Ionization potential is also known as ionization energy or ionization enthalpy. As the name suggests, it is a type of energy. But what type of energy? It is the energy which is required to remove an electron from a neutral isolated gaseous atom and convert it into a positively charged gaseous ion, and this energy is known as ionization potential or ionization energy. So whenever there is an atom and that atom loses an electron, it becomes a positively charged ion or a cation. So the energy required to remove that electron from the atom, that energy is known as ionization energy. So as the definition suggests, we can very well understand that ionization energy will be very less in case of metals, because metals can easily lose electrons, but the ionization energy will be very high in case of non-metals, because non-metals do not have a tendency to lose electrons. So even if they want to lose electrons, we have to apply a lot of energy. So this is all about ionization energy, and its SI unit is kilojoules per mole, because it is the amount of energy required to remove some particle. So kilojoules per mole. So ionization energy, just like any other periodic property, depends upon atomic size and nuclear charge. So how does it depend? We will see in the next slide. But before that, there is a very important thing over here. The second ionization energy is always larger than the first ionization energy. So what is the second and first ionization energy thing? For example, let us consider magnesium. Magnesium has 2 electrons in its valence shell. So it will remove the first electron very easily because it has a tendency to do so. So the amount of energy required to remove the first electron out of the 2 electrons in the valence shell, that is known as first ionization energy. And now in order to remove the second electron from the valence shell, the amount of energy that has to be applied, that is known as the second ionization energy. So removing the first electron is much more easier as compared to remove the second electron, because when the second electron is getting removed, we are not removing it from the atom, we are removing it from the ion. So the first ionization energy is always smaller compared to the second ionization energy. In order to remove the second electron from the atom, you have to apply much more energy. This has been written out here. Very important observation. Next is the trend, which is followed by the ionization potential across a period and down a group. Across a period, the ionization energy tends to increase as one moves from left to right. Why does it happen? Because we know when we are moving from left to right in a period, the metallic character is decreasing slowly. We are moving towards non-metals. Also, the size decreases, and as a result, the nuclear charge will increase. So if the nuclear charge increases, it is very difficult to remove the electron. And if it is more difficult to remove the electron, the amount of energy which will be required to do so will be too much. So the ionization energy increases as we are moving across a period. But down a group, what happens? The size of the atom is increasing, and as a result, the nuclear pull is very less. So the outermost electron can be very easily removed. We don't have to apply a lot of energy. So the ionization energy or the ionization potential decreases as we move down the group. So whatever periodic properties we will study, we will always explain it on the basis of nuclear charge and the atomic size. Next, we have another very important observation. Helium will have the highest ionization energy, while cesium will have the lowest ionization energy. Cesium 1 is very easy to understand because it is the best metal, so it will have the lowest ionization energy. It can very easily remove electron without much energy requirement. But what about helium? As we know, noble gases do not react with anything, they are stable. So obviously, to remove an electron from a noble gas, it will be a great task. We have to apply a very high amount of energy. And out of all the noble gases, since helium is at the topmost position, so it has a very strong nuclear pull also. So these two criteria add up to the high ionization energy of helium. And we see that in the first group there is another element called francium, but we don't consider it in the periodic properties which we are learning, because it has radioactive properties and its properties are a little different from the normal elements which we study. Metals generally have low ionization energy or low ionization enthalpy, like I told you, because they are able to very easily lose electrons. We don't have to apply a large amount of energy to them. But in case of nonmetals, since nonmetals do not have a tendency to lose electrons, a large amount of energy is required to remove electrons from them. So they have a high ionization energy. So this is all about ionization energy. Our next periodic property is electron gain enthalpy or electron affinity. Saying electron affinity is much more easier to understand because electron affinity means affinity towards electrons, liking towards electrons. And who likes electrons, who wants to take electrons? Non-metals, obviously. So we can very easily understand this characteristic in that way. The amount of energy released while converting a neutral gaseous isolated atom into a negatively charged gaseous ion by the addition of electron is known as electron affinity. In the previous case, we saw that the neutral atom was converting into a positive ion. But in this case, the neutral atom is converting to a negative ion by taking electron. So the amount of energy released in this case, that amount of energy is known as electron gain enthalpy or electron affinity. So obviously electron affinity is more for non-metals and less for metals. We'll see what will happen when we move across a period and when we move down the group. So it also has the same SI unit, kilojoules per mole, and it also follows the same trend, that is across a period the electron affinity will increase because we are moving from metals towards the non-metals, and non-metals have a high electron affinity. So obviously the electron affinity will increase as we are moving across a period. And down a group, what happens? Down a group the metallic character increases. As a result, the electron affinity will decrease. The same reason again, down a group, let's see once again. Down a group, what happens? The size of the atom will increase. As a result, electrons can be lost easily. Nuclear pull is so less. So how will electrons be gained? So obviously electron affinity is decreasing. So there is a very special characteristic which we are going to learn regarding fluorine and oxygen. So in group 17, fluorine is at the topmost position. So as a result, it should have the highest electron affinity because just we saw that electron affinity decreases down the group. But what has been said, let's see. In group 17, fluorine has lower electron affinity than chlorine, and also in group 16, oxygen has lower electron affinity than sulfur. Both of these are the first elements of their respective groups, but instead of having the highest electron affinity in that particular group, it has a little lower than the second element. Why does it happen? Very simple. Fluorine and oxygen are very small in size, very small. The atomic size is very small. As a result, all the electrons in it are placed very close to one another, and if two like charges are placed close to one another, they will have repulsion. So due to this inter-electronic repulsion between the electrons of fluorine and oxygen, they are not able to easily accept an electron coming from the outside. So their electron affinity is a little less compared to their next element itself because of their size. You will learn about this more in class 12. There is another question which can come to your mind, that why do we consider a gaseous atom, or why do we consider a gaseous ion in both the definitions of electron affinity and ionization potential? What is the reason? Let's see. The reason why ionization energy or electron affinity is measured in the gaseous phase is because in the gaseous phase there is very little attraction between the other particles which affects the ionization energy. Between the other particles which are present in the matter, there is a very little amount of attraction. So to understand these properties, it becomes much more easy for us in the gaseous phase. And in the gaseous phase, when we do these studies, the results are much more accurate. So gaseous phase is considered for observation. This is the last periodic property which we will learn. It is called electronegativity. It is a tendency, it is not a real phenomena, it is actually a tendency of the atom in a molecule to attract the shared pair of electrons towards itself. And this is a dimensionless property because it is imaginary, it is just a tendency, it is not happening in real, so therefore it does not have any units. So what happens whenever a covalent bond is formed, a polar covalent bond is formed, the element which has much more tendency to attract the pair of electrons towards itself, we will see that the electron cloud gets shifted towards it. You will study about this in much more detail in the second chapter though, but what happens? It happens only in case of covalent compounds, polar covalent compounds specifically. So for example, HCl is there. So H will give one electron and chlorine will give one electron. They will share it basically. So both of them are satisfied in the valencies. Since chlorine is much more electronegative than hydrogen, the shared pair of electrons will be shifted a little bit towards chlorine. The same thing happens in case of water also, both of which you will learn in the chapter bonding. So across a period and down a group, the same thing happens just like the previous two cases. Across a period, electronegativity increases because electronegativity is specially a property of non-metals. So as we are moving towards non-metals, it will obviously increase. And down a group, electronegativity will decrease. Generally, metals have lower electronegativity and non-metals have higher electronegativity. Therefore, we say that non-metals are electronegative, but metals are electropositive. The topics which you have studied in the lower classes, now it is going to be much more clearer. So, electronegativity is generally a tendency of non-metals only. So, there is another very interesting thing which is known as diagonal relationship. This is not a periodic property, this is just a fact. The elements of the second period show resemblance in properties with the elements of the next group of the third period due to the very less electronegativity difference. This leads to diagonal relationship. As you can see, we have considered period 2 and period 3. We have lithium, beryllium, boron, carbon, and sodium, magnesium, aluminium, and silicon. According to this diagonal relationship, what happens? Lithium bears some similarity in properties with magnesium. Similarly, beryllium bears some similarity in properties with aluminium, and boron and silicon are also similar in properties. Why does it happen? Because they have very small electronegativity difference in between. So since they have this diagonal relationship, they are also known as bridge elements. There can be a question asked in the board examination, what are bridge elements? So you have to say this. And what is the condition for this diagonal relationship? It is because of the small electronegativity difference between those elements. I hope it is clear till here. Next, we are going to learn about a very simple and known topic to you, atomic number and mass number. So what is atomic number? We know that the number of electrons and the number of protons in a neutral atom is same. But we always say that the number of protons is equal to the atomic number. Why does we say this? Because we know whenever a bond is being formed, electrons are lost. So electron number can change, but proton number will never change. So something which is fixed, we consider our properties in such a way. So atomic number is the number of protons which are present in the atom. And what is mass number? Mass number is the total amount of substance which is present in the nucleus. That means we know in the nucleus neutrons and protons are present. So the total number of protons and neutrons in an atom, in the nucleus of an atom rather, that is known as the mass number. Atomic number is denoted by Z and mass number is denoted by A. Whenever we write an element, for example, we are writing sodium. The number which we write at the top, that is the mass number, and the number which we write at the bottom is the atomic number. Since mass number varies in isotopes, that's why mass number was not considered to be a better option for understanding the periodic table or for making the periodic table. Therefore, atomic number was used and mass number was discarded. Now we see a very interesting thing out here. If you look at the electronic configurations of the lighter elements means whose mass number is low. We see that elements which have even number of protons, that means whose atomic number is even number, they will have their mass number almost twice of their atomic number. For example, helium has an atomic number of 2 and it has a mass number of 4, double of atomic number. Similarly for carbon has an atomic number 6 and its mass number is 12. It is not fixed for every element, there can be exceptions. So as you can see, there are exceptions like beryllium and argon. Beryllium has an atomic number of 4 but its mass number is 9, which is not double. And similarly, argon has an atomic number of 18 but its mass number is not 36, it is rather 40. So there are exceptions obviously. Also in elements which have odd number of protons, we see that their mass number is actually the twice of the atomic number plus 1. Let's see some examples. Lithium, it has an atomic number of 3, so its mass number is 2 into 3 plus 1, that is 6 plus 1, 7. The same thing is applying for boron, fluorine, sodium also. But there are also some exceptions in this case. For example, nitrogen, its atomic number is 7 but its mass number is not 15, rather it is 14. So exceptions are always there, but if we look closely we can find some similarities also. Also in elements where the neutron-proton ratio is around 1, if you consider the number of neutrons and the number of protons and you find their ratio and it is almost equal to 1, like 0.9, 1.01, these type of elements are stable. They do not show any type of radioactivity. Now what is radioactivity? You will study about this in much more detail in physics, but let me just tell you a little bit about it. Sometimes what happens, there are certain elements, generally the heavier elements, when we place them just like that without heating it or without applying any sort of energy, they will start emitting radiations, alpha particles, beta particles, gamma radiations, etc. So these type of elements are known as radioactive elements. So in case of elements where the N by P ratio is almost equal to 1, they do not show such radiation. But whenever their NP ratio is more than 1.5 or it is 1.5, what happens? They will start emitting radiations. They are very unstable in nature. Unstable in the sense that whenever you keep them in a space without applying any sort of energy to them, they will start disintegrating. They will start losing these type of particles from them. This video marks the end of this chapter, and if you have any doubts regarding this video or the previous lives which we have done, you are free to send us your doubts in the email which has been provided in the description box. And from the next day we will start with a new subject and a new chapter, and I'll try to bring a question session for this chapter where we will do all types of board exam pattern questions for a better understanding of the chapter. Thank you so much for listening patiently.